In section 6.2, we learn how to compute atomic and molar masses. It's important to recognize that 1 mole of an atom weighs an equivalent number of grams as the mass of one atom in AMU. We give the name for the mass of 1 mole of a substance as its molar mass. So for example, we know that 1 carbon-12 atom has a mass of 12 AMU, which means if we have a whole mole of carbon-12 atoms, according to this statement up here, then that mole of carbon-12 atoms will weigh 12 grams, or we could say that the molar mass of carbon-12 is 12 grams per mole. So it's important to recognize that the molar mass has the same value as the formula mass of a compound or the atomic mass of an atom, but its units will be grams per mole. For example, as we already stated, 1 carbon-12 atom has a mass of 12 AMU. 1 mole of carbon-12 atoms has a mass of 12 grams. Therefore, the molar mass of carbon-12 would be 12 grams per mole. According to the periodic table, 1 sodium atom has a mass of 22.99 AMU. Therefore, I know that 1 mole of sodium atoms has a mass of 22.99 grams, or we could say that the molar mass of sodium is 22.99 grams per mole. A chlorine atom, according to the periodic table, has a mass of 35.45 AMU. Therefore, I know that a whole mole of chlorine atoms will have a mass of 35.45 grams, or I might say that the molar mass of chlorine is 35.45 grams per mole. So this is a simple example from the textbook. It's asking for the mass of each quantity. And the first one says 1 mole of gold atoms. So we need to find gold in the periodic table and note down the mass of 1 gold atom. So 1 gold atom has a mass of 197.0 AMU. Therefore, 1 mole of gold will have a mass of 197.0 grams. So that was easy, 197.0 grams for the first one there. According to the periodic table, 1 bromine atom has a mass of 79.90 AMU. So that means that 1 mole of bromine atoms has a mass of 79.90 grams, and then 5 mole of bromine would have to have a mass of 5 times 79.90 grams, and putting that into the calculator, 5 times 79.9, that gives me a mass of 399.5 grams. So pretty simple concepts. We can just use the periodic table to identify the molar mass of any element. For molecular compounds, 1 mole of the compound weighs an equivalent number of grams as its formula mass in AMU. So it's slightly more complicated. The first thing that we'll need to do is to calculate the formula mass of our compound. So for water, for example, we're going to add together the masses of 2 hydrogen atoms and 1 oxygen atom to get the formula mass of water in AMU. And what that's really telling us that if one water molecule weighs 18.016 AMU, then a whole mole of water molecules will weigh 18.016 grams, or we can say the molar mass of water is 18.016 grams per mole. So it's important to recognize that the molar mass, whether it's for an atom or for a compound, can function as a conversion factor between the mass in grams and moles. So, as we did previously, we can calculate the molar mass of water by summing together the masses of the atoms that are in its formula. So we've got 2 hydrogen atoms plus an oxygen atom, gives us a molar mass of water of 18.015 grams per mole. And this molar mass can be reorganized to give 2 conversion factors. This first conversion factor here cancels moles and turns moles into grams, and the second conversion factor cancels grams and turns the grams into moles. So depending on what you want to do, you can use the molar mass in 2 forms. So here's an example problem. It says, how many moles are there in 2.54 grams of water? And so we recognize that we're going to do a conversion from grams into moles. And to do that, we're always going to use the molar mass. So we can go ahead and calculate the molar mass. And all we did here was, just like we'd done previously, added together the masses of 2 hydrogen atoms and 1 oxygen atom, because that's what's in the formula for the compound. And we are starting with 2.54 grams, so we need to use the conversion factor that has grams on the bottom line, and we want to turn it into moles, and it needs moles on the top line. So we're going to flip this guy up here to have the conversion factor in the correct form. And now when I multiply, my grams will disappear, and the only unit that remains is the moles. So I'll just put into my calculator 2.54 times 1 divided by 18.015. So let's see if we can do this problem from the book. It says, what is the mass of 1 mole of each substance? And so all I've got to do here is find the atoms that are in the compound in the periodic table and make sure that I add them up correctly. So we need barium, sulfur, and oxygen to answer the first one. And I've got to add together the mass of 1 barium plus 1 sulfur plus 4 times the mass of oxygen. And let's see what we get. 137.3 plus 32.07 plus 4 times 16. And we got 233.37 grams. You can try the next one. It's a little bit more complicated. We need carbon, hydrogen, nitrogen, and oxygen. So we need carbon, hydrogen, nitrogen, and oxygen. So we have 10 times the mass of carbon plus 13 times the mass of hydrogen plus 5 times the mass of nitrogen plus 4 times the mass of oxygen. So 10 times 12.01 plus 13 times 1.008 plus 5 times 14.01 plus 4 times 16. And so I ended up with 267.25 grams. And so there we go. All right, so make sure you give your number a unit. we're calculating the mass in grams in this case. So just doing a little bit of housekeeping here. Avogadro's number is the number of carbon-12 atoms measured to be present in 12.000000 grams of carbon-12. And the most up-to-date value for it is 6.0221415 times 10 to the 3. 10 to the 23, not 10 to the 3. That would be a horrible error. However, while that's the best value that we've got for Avogadro's number, chemists normally just use 6.022 by 10 to the 23. That is, they normally just use the number good to 4 significant figures, and then they treat it as an exact number. That is, we're going to treat this number here as though it has infinity significant figures. Whatever the situation that you're in, just please use the value of Avogadro's number that's given to you and the number of significant figures that's provided. That way, there won't be any issues with rounding errors and things like that. So, 2 key points that are worth noting at this point. Avogadro's number is the conversion factor that allows us to convert between moles of something and the number of objects in a sample, whereas molar mass is the conversion factor that allows us to convert between moles and the mass in grams. One interesting little thing that we can do is to derive the relationship between AMU and grams. So for example, I know that there are an Avogadro's number of carbon-12 atoms in 1 mole of carbon-12. I also know that there are 12 AMUs for every 1 atom of carbon-12. And I know that in 1 mole of carbon-12 atoms, there is 12 grams of carbon-12. So we put all of this together in such a way that the units cancel out, and we end up with a relationship between AMU and grams. And what it tells us is that there is an Avogadro's number of AMUs in 1 gram. Or you could say in 1 gram, there is an Avogadro's number of AMUs. And this is a much more convenient way of convenient conversion factor for converting between grams and AMU. So, this question asks, how many grams does a molecule with a mass of 105.42 AMU weigh? And of course, molecules don't weigh many grams, so we're expecting a very small number. So I'm going to take my 105.42 AMU, and I'm going to multiply by the conversion factor that has AMU on the bottom line and grams on the top. And when I do this, AMU will cancel out, leaving only grams, and the answer I get from my calculator is indeed a very, very small number, which is not surprising because we're talking about a single molecule, which is just a small number of atoms. And that concludes section 6.2 concerning atomic and molar masses.